We all know about flywheel. The moment we hear the word flywheel, we immediately think about IC engine, and its role is very fascinating. Please understand that we always give some input power to a mechanical system in order to achieve some output motion. In many situations, either the power input or the required power output are not constant. They are fluctuating. In such scenario, we will be needing a component, namely flywheel. Flywheel is a fascinating mechanical energy storage reservoir. You all know that. In this video, we will be exploring more about flywheels so that we should be able to design it eventually. Yes, let's get started. Hi everyone, welcome to my channel. It's me, Dr. V. Jayakumar, making lecture videos for the benefit of mechanical engineering students. If this is your first time not yet subscribed, please do hit the subscribe button and also the notification bell icon so that to get notified all my forthcoming videos. Yes, these are the learning outcomes. What is a flywheel after all? What is it? It's a battery. What it does, it stores electrical energy in a chemical form. In the same way, flywheel stores mechanical energy in the form of kinetic energy, right? Let me give you a few more analogy to flywheel. You might have heard about a capacitor in a AC or DC circuit. What is the role of the capacitor? Capacitor simply stores charge and discharges quickly into the load whenever required. Do you know the role of the accumulator in hydraulic circuits? Accumulator stores and discharges energy in the form of pressurized fluid. Same way, we have flywheel, which stores kinetic energy whenever we have in excess and gives the same whenever it is required. So it is a mechanical energy storage device. Fine? Yes. Functions of a flywheel. Of course, to store mechanical energy, but its most important function is to smooth speed fluctuation in a machine cycle between the power source and its output. Flywheel does not maintain a constant speed. It simply reduces fluctuation of speed within the cycle. This is the definition mechanical engineer is expected to tell. First, let us understand clearly, where do we need flywheels? So there is an input power which is fed into a machine, and there will be an output power. These are the two things involved. Of course, there will be some losses along the way, but for our studies, let us ignore the losses. Let us concentrate on only those two things, input power and output power. In the first category, we will be having a fluctuating input power, whereas the required application output will be constant. Let me draw a graph wherein in the x-axis I have taken time, in the y-axis I have taken a power. So for a machine, what happens to the power input? It varies over the time. Power input is fluctuating. Whereas the yellow dotted line shows the application load, required power output. Required power output is constant. So how can I satisfy the demand? This is where flywheel comes into picture. Can you name some applications where we have fluctuating power input? Yes. The most popular example is internal combustion engine, where we are not getting the power from the IC engine continuously, constantly. It is a fluctuating power. We are getting the power only during the power stroke, mind you. So in this case, it demands flywheel to serve the purpose. Right? It is an actual picture of an automobile engine. In this category, as you could see, this is the flywheel. We have an engine here. This is the flywheel. So here, engine produces fluctuating power input, whereas my record output torque is constant. Okay? Let me give you another example. In the conventional sewing machine, the input power will not be constant. The pedaling cannot be constant. So there is a varying input power. So literally, these two wheels in a way serves the purpose of a flywheel. Is that clear? Now let me go to a second category, wherein I have some few machine applications where input power is constant. So input is a constant power input, whereas output power record is fluctuating as shown in the yellow color line. In that case, again we need flywheel. Is that clear? Can you think of some applications for this category too? Punching presses, reciprocating compressor, reciprocating pump. There are many applications. What is that? Very popular punching press, which is driven by an electric motor, by a constant power input electric motor. But what happens to the punching operation? During punching operation, only at the moment of punching, we need enormous energy to punch the workpiece. For the rest of the stroke, literally, not much energy is required. So that means the energy required by the application is fluctuating drastically. So we need flywheel in between them. Okay? Yes. These are some pictures of shearing machines. You can very well see the flywheels, the huge wheels are being designed or being installed as part of those machines in order to do the same purpose. Then you might have seen on the roads, right, some sugarcane crusher machines. Similarly, some stone crushers. There are many types of crushers are being used for industrial applications. All that invariably are using flywheels in them. Clear? Now, let us take a car. You might be curious to know where a flywheel is located. Flywheel is mounted as part and parcel of the crankshaft. So speed of the crankshaft and the speed of the flywheel are essentially same. In a car, the flywheel is mounted on the back side of the engine. So flywheel is the mechanical member which will be coming into contact with the clutch. So we have crankshaft. Back end of the crankshaft will have flywheel. Flywheel will be connected with the clutch. Then from there on, we will be having the gearbox. Now you are very clear with the location of the flywheel in a car. So what would be the shape of the flywheel? What are the various types? This would be a typical flywheel used in an engine. Can you guess the reason why? It has tooth cut on its periphery. Any guesses? We need to start the engine first before flywheel starts storing some energy. So we need to start it. For that we have starter motor. Low RPM starter motor end we have a smaller pinion which will be in turn directly connected with the flywheel. Because of the smaller pinion and bigger flywheel, we will be getting higher torque which will be helping to crank the engine, to start the engine. Before going further, we need to introduce now turning movement diagram. We have already studied in force analysis of reciprocating engines. The most important component is torque exerted on the crankshaft. In other words, turning movement of the crankshaft. In fact, we have derived the equation for it. This is the equation. Here you can very well understand that the turning movement of the crankshaft varies with respect to theta. To capture the variation, I can draw one graph. That graph drawn by taking crank angle in the x-axis and turning moment in the y-axis, the diagram obtained is known as turning moment diagram. Actually, what we are having is nothing but a typical turning moment diagram for a single cylinder 4-stroke IC engine. By using the earlier formula, for the various theta values, we can easily determine corresponding t values. Using those theta and t values, we can very well draw this turning moment diagram. Is that clear? Yes. What is the use of turning moment diagram? This turning moment diagram will be very crucial for us to design the flywheel, which we will be dealing in next few videos. For many of us, it's very difficult to physically visualize, feel how a simple wheel stores mechanical energy, isn't it? We will try to explain that phenomenon. We will try. For that purpose, let us take single cylinder 4-stroke engine. So it's very clear that only during power stroke, we are getting useful power, energy. Whereas in other strokes, we need to spend the energy to get those operations done, to get those strokes completed. Am I right? So what happens? The power produced during the power stroke should be used for two purposes. First purpose, to supply the application demand, to run the automobile. Then some portion of the power obtained will be stored in the flywheel, which what we call excess energy. That excess energy will be used up, will be supplied during other 3 strokes, namely suction, compression and the exhaust strokes. Is that clear? Yes. This turning moment diagram will make us to understand this concept still better. As you could see, only during the working stroke, power stroke, we are getting very high turning moment. Whereas during suction, compression and exhaust, we are spending turning moment. That is the reason why you can see compression in negative loop. Some portion of the suction and the exhaust are in negative loops. In the diagram, the second part of the suction stroke results into some small positive loop. That is because the fresh incoming air helps in exhausting the flue gases some way. It does some useful work. That's why some small positive loop is given. Similarly, the second part of the exhaust stroke results in some positive loop. Because of the pressure difference, some of the exhaust gases are exhausted out without consuming some external energy. Is that clear? This is turning moment without flywheel. Before going to that, we must be understanding clearly about one more line, the horizontal line, which we call it as a T-mean line. That is the constant application output torque required from that engine. So that means over and above T-mean line is considered as excessive. Below the T-mean line are considered as deficient. Is that clear? So as you could see here, only during the power stroke, we are having some surplus energy. During all other 3 strokes, we have deficient energy. This is without flywheel. And now I am taking the flywheel and mounting it on the crankshaft. Yes, there you are. You could see turning moment diagram of the engine with the flywheel, which is shown in a red turning moment curve. So we have 2 curves in the same diagram. One is the turning moment curve shown in the black letter, that is without flywheel. There the fluctuation is enormous. In the red one, you can see the fluctuations is evened out. What could have happened? Simply installing a flywheel, we could get this diagram. What could have happened? What could have happened is, this portion surplus energy that we have obtained during the power stroke should have been stored by the flywheel in the form of kinetic energy. That kinetic energy, excess kinetic energy, might have been distributed to exhaust, suction and compression, and hence it evens out. Interesting, isn't it? Here let me bring you one concept. What is the function of the flywheel? To reduce the speed variations within a cycle. What the engine we have taken is a single cylinder 4-stroke engine. What is it by cycle? For every 2 rotation of the crankshaft, for every 720 degree rotation of the crankshaft, we will be getting 1 power stroke. That is the cycle of 4-stroke engine. So it's very important that we must be drawing the diagram for a cycle. So within a cycle, the excess energy stored by the flywheel should be supplied to other stroke, and hence at the end of the cycle, there should not be any energy stored. Clear? That means if I put inappropriate flywheel, which might store more energy, what will happen? If I store more energy, only some portion of the energy is being spent. That means over each cycle of operation, energy is being stored more and more. Speed will be increasing more and more, which will fed into the mechanical system. Eventually it will fail. That means we have to find optimum flywheel size. Do you know this cycle which we are talking about, 4 strokes, the energy storage and supply of the excess energy to rest of the strokes are happening in a fraction of seconds. Let us assume that engine runs at very low RPM for our case. Say 600 RPM is the engine speed. The meaning of 600 RPM for a single cylinder 4-stroke engine is 5 cycles per second. Or in other words, 1 cycle will be completed by 0.2 seconds. What I mean to say, my dear friends, is all are happening in a fraction of a second. So similarly, I could draw turning moment diagram of a single cylinder double acting steam engine. Anything above output torque line is excess, below the torque line is deficient, right? If I take the crank position from I to J, we can say what is actually produced? Area under IA, BC, J. What is actually required? Up to T mean line. IA, CJ is required. That means this shaded line is circular energy. This is a typical 3-cylinder engine turning moment diagram. As you could see there, the fluctuation is not so enormous as in case of single cylinder engine. That is the reason why multi-cylinder engine will require smaller flywheel when compared to that of the single cylinder engine. Is that clear? Yes. What will be the turning moment diagram of a electric motor? Turbine. It's a constant RPM motor. Obviously, it will be a flat straight line. There you are. These are the key takeaways you should always remember. We will be designing a flywheel for a given application with the help of turning moment diagram, which we will be studying in our forthcoming videos. Oh, now you got clear picture about the flywheel, isn't it? If so, do not forget to like the video, share to your friends and subscribe the channel. So let me catch you in my next video. Thanks for watching. Take care. Bye.